So hello everyone, welcome to all of you in my lecture today. Okay, I am going to teach you today the transfer function for the mixing process. Okay, so before I am going to derivation part, I am letting you to understand which types of things that I am going to discuss in this lecture today. That I will be taking a simple mixing tank for a single component system only. There won't be any chemical reaction that will be taking place inside the mixing tank. Okay, only we are agitating the amount, we are agitating the component with the help of stirrer, and the component will become will get well mixed, and after that we will be calculating the output response or output concentration. Okay, where after a particular time while changing in the input concentration. Okay, so just try to understand in which way we have to drive. Okay, after that I will tell you which types of question that can be asked here. This is a mixing tank. Okay, now here the component is going to enter in this particular tank, and here the component is going to be out. This is V naught, this is the volumetric flow rate of component 1, and C1, that is the inlet concentration. And here we are going to maintain the volumetric flow rate, inlet and outlet is same. Then the calculation becomes very easy, and C2 is the outlet concentration. So here I am writing, here it is inlet concentration of the component that is going to enter in the mixing tank, and C2, that is outlet concentration. Okay, that is the outlet concentration. These two things that you have to understand first. Now that I am writing V naught, that is the volumetric flow rate. Okay, that is volumetric flow rate of the component that is going to enter into the mixing tank. Now, my dear student, try to understand. There is only single component. Just try to understand here. Only A is going to enter. Okay, in this particular mixing tank, it will get mixed, and after it will be coming from the out of the reactor. Then you can apply the mass balance for component A. Mass balance. Okay, it will be very easy. Mass balance for component. Okay, here I am taking only one component. Okay, for single component only. Okay, there may be more than one component. Okay, but I am taking only one component. Okay, if you know the basics of the single component system, then definitely you will be able to derive the the transfer function for the various two component system. I don't think in get two component system will be asked, because single component is much more tedious, so you don't have to go to two component system. Okay, and now try to understand. If you will see, then here inlet in minus out, that is equals to accumulation only. Why I am writing only accumulation? Because my dear student, this is only a simple mixing tank. There is no any chemical reaction that is going to take place. So there won't be any chemical reaction. So there is no any substance that is going to be produced, or there is no any substance that is going to be disintegrated. Here only the component is going to be well mixed. So whatever the component is going to be in minus whatever the component that is going to be out, that will get accumulated inside the tank. Also here you can write V naught C1 minus V naught C2, that will be equals to d upon dt of m. Okay, d upon dt of, here this is a mass flow rate, here this is also a mass flow rate, it will be also a mass flow rate. Okay, I think up to this you all have clear now. My dear student, after that if you will see V naught, if you will take V naught common, then you will be getting C1 minus C2, that is equals to d upon dt of m. From here, if you will go, that is nothing, this is totally a mathematical part. If you will see C1 minus C2, here you can write that is m into v, or you can write here uh, here you can write directly. I am writing d upon dt of volume into c, because we are going to assume constant hold up system. So this will be the volume of the reactor. Okay, or sorry, volume of the mixing tank. Okay, so from here you can write, okay, v into c. Now here, from here you can, if you will take v naught common, then you can write v upon v naught of d upon dt of c2. Why c2? Why I am writing here c2? Because the substance inside the reactor will get well mixed. So here you will be getting a concentration c2, and again here also you will be getting a concentration c2. So that you need to focus here, that okay. Nothing else I am going to discuss, only this is simple thing. Now from here you can derive the thing C1 minus C2, that is equals to tau and dC2 by dt. Okay, and here if you will see the tau value, tau is equals to v1 v upon v naught. Okay, now understand tau, if you will write tau dc2 upon dt plus c2, that is equals to c1. So my dear student, if you will see from here, this will be a transfer function of first order, and already you know how we used to derive the transfer function, the transfer function from the first order differential equation. If you will take Laplace, I am taking here, taking Laplace transform, taking Laplace. Okay, if you have remembered the formula of Laplace for the differential form, okay, then definitely it will becomes very easy. Tau s, c2s, tau s c2s plus c20, that is equals to plus c2, okay, is equals to, my dear student, c1s in the deviation form. So c2 at t is equals to 0, at I am here writing at t is equals to 0, c2 is equals to 0. These things that you need to understand here, that's nothing. At t is equals to 0, only reactant will be entering, there won't be any outlet. Okay, that's why c2 will be 0. So from here you can write, that's easy. Tau s, if you will take common, tau s plus 1, that will be equals to c2, that is equals to c1. I am writing it in the deviation variable form. Okay, so here from here you can get c1 upon c2 upon c1, that will be equals to 1 upon tau s plus 1. So my dear student, this is our desired derivative, the transfer function of our mixing tank. Okay, so here you can write tau is equals to v by v naught, means volume of mixing tank, volume of mixing tank upon V naught, that is equals to the volumetric flow rate. Okay, this will be used in if you will be studying the chemical reaction engineering, then definitely there you will get aware about this particular term. This is called a tau. Okay, so from here you can write the outlet concentration in the mixing tank upon inlet concentration, that is equals to 1 upon V naught into s plus 1. So this is our desired transfer function, my dear student. If you will say, just understand one thing how it will work. So c1, if understand one thing how we are going to relate these things with our output, that's main concern here. If we are going to give the step input, if you will see before going to next part, if you will see from here, then definitely you will be getting, this is the first order transfer function. Okay, here this is the first order transfer function, this is inlet concentration, this is outlet concentration, that is our desired response. Okay, this is c1 and this is c2, and if a steady state C1s, if C1s will be equals to 0, then at t is equals to 0, if you are giving a step input of m, a step input of magnitude of m at t is equals to 0, then how the output will respond from here, already you know this thing. If this is C1, okay, I am writing it in the deviation form, and the steady state value, this is 0, so you can write C2 at any time t, okay, minus c2 at a steady state, that is equals to m into 1 minus e की power minus t upon tau. This will be the response of the mixing tank, means this will be the response of the mixing tank if you will be applying a step input at the inlet of the concentration. Okay, so how this response will be, that's major concern here. So the output response will be like that. So at t is equals to infinity, at t is equals to infinity, what will happen, this term will become 0. Okay, so at t is equals to infinity, c2 infinity, that is equals to how much, to m. So just understand one thing, if this value is m, then this will be increasing and increasing, and it will be like that, and it will be increasing exponentially, and at t is equals to infinity it will be tending to the value of m. So my dear friend, this is the response of our the mixing tank process. Now which types of question that is going to be asked, that's the major concern here, because derivation part is I think up to clear to all of you now. Now I'm going to discuss which types of question that is going to be asked in the gate examination. Understand, the gate examination will be giving, that is a mixing tank, that will be the inlet concentration, that will be the outlet concentration c2. Okay, so they will be giving c1. Okay, now volumetric flow rate, just try to understand, they have given 2 meter cube per second, and volume of this mixing tank is given 2 meter cube. So from here you can calculate tau is equals to v upon v naught. That's very easy calculation, is not difficult. I have taken the simple numeric value. That's why it's very easy, and GATE won't be asking these things tedious. They won't be giving tedious calculation. Okay, now you have calculated down. Now they are telling a step input of magnitude 2. A step input of magnitude 2 is applied at C1. C1, you are going to apply C1 at a step input. Then they will be asking calculate the outlet concentration at t is equals to 2 seconds. Okay, so how you will calculate? If outlet steady state value is 0, that is equals to C1, okay, m into 1 minus e की power minus t by tau. So from here you will be getting C2 at time 2 is equals to m value magnitude is 2. A step input will be like that. Here they are giving 2 in step input in concentration at initial state. So you will be getting 2 into 1 minus e की power tau value you have calculated. They are asking about t equals to 2 second e की power minus 2. So from here you can calculate this value from the GATE calculator. So these types of question they will be asking. Okay, the small question that can be asked here. Now understand one thing. I think the transfer function and which types of numerical that can be asked in the GATE examination. It's all for all of you. It's very clear to all of you. Now I am going to discuss some different part. Okay, that is also related to the transfer function, and it's important. Already GATE has asked these types of question once. Okay, so they have asked only the derivation part up to this. Which types, which topics that I am going to teach you right now. Okay, now so how we will take. So just understand one thing. So if there are two input variables, if there are two input variable, if there are two input variable, my dear student, already up to this whatever the derivation part that we have seen, either that is related to the energy capacity system, or either that is related to the continuous state tank reactor, or that is the mixing tank that I have discussed right now. Okay, if they all are related to only single component or single input system. Now I am going to discuss if there are two input that is given in the system, then which how will we calculate the transfer function, because the transfer function, the output of the system, that will depends upon our two input. Okay, so the both input is going to affect our system, and after effect if the system is get affected by our two input, then definitely the output response will totally depends upon our input. Okay, so how we will calculate these things, just understand. If you will say the transfer function like that, tau dy upon dt plus y, that is equals to k1 x1 plus k2 x2. These types of transfer function, that first order differential equation, if you have watched, if you will see in the question, then definitely if there is a first order differential equation, then that will be making a first order transfer function. First thing. Second thing is that here if you will see there is x1 and there is x2, you will see there is two input in this transfer function. Okay, so if you will take Laplace transform, so from here you will be getting tau s, here ys minus of y0 plus ys, that is equals to k1 x1 s plus that is equals to k2 x2s. After taking Laplace you will be getting these types of things. Okay, so if you will take common ys, this will be 0, there won't be output any output that is equals to 0. Okay, so if you will see here, from here tau s plus 1 into ys, that is equals to k1 x1s plus k2 x2s. These things that you will say. So here from here ys upon x1s, okay, that you will see k1 upon tau s plus 1. Here just try to understand, so many students used to do some fault here. Here I am writing ys upon x1s. My dear student, this is x1s, that there are two input. I am going to show these things pictorially. Then you will be getting something good idea, so some good visualization. Okay, this is tau s ys by xs 1s, that is equals to k1 upon tau 1s. This is k1. This is the gain of the process. First, second thing is that again second input is there also. So here you can write ys upon x2s, that is equals to k2 upon tau s plus 1, k2 upon tau s plus 1. So what is the difference between these two output, just try to understand our ys, that is going to depend upon, if you are going to change a step input in x1, then you will be getting a different output. Then you are going, if you are going to change different input in the x2, then definitely you will be getting different output. Okay, so these types of system is called as the multiple input system. Here you are giving two input and you are getting a single output, means multiple input and single output system. You can understand these things from here. Now understand one thing, my dear student. If it's very clear to all of you, I am going to draw these things with the help of the figure. Pictorially I am going to define these things, then it will be very easy to understand to all of you. This is plus and this will be plus, this is okay. Now here understand, this is x1s and here this will be the x2s. Okay, and here you will be getting ys, here you will be getting ys. So from here you will be getting k1 upon tau s plus 1, and from here you will be getting k2 upon tau s plus 1. So my dear student, from here you will be getting ys that is equals to ys, that is equals to either you can write it uh, k1 upon tau s plus 1. uh, I am unable to write here. Okay, there is some technical problem. Okay, I am just going to change it in this direction, then definitely it will be easy. So from here you will write ys, that is equals to k1 upon tau s plus 1 into x1s plus k2 upon tau s plus 1 into x2s. So this will be our output response. Now from here, from here if you will see, then from here if you will see this output response, then your output response is going to depend upon both x1 value and x2 value. If you are going to change these two both, then your output will be get affected. If you are going to change x1 only, then output will get affected. Then if you are going to change x2 only, then definitely output will get affected. So this is the type of system that we use to call it as a multiple input single output system, and this is called as the multiple input MISO. MISO means that is multiple input and single output system. I think, hope so, this concept is very clear to all of you, my dear student, because I am going to teach you, I will be teaching next in my next class, that is a steer tank heating system, where you will see these types of multiple input and single output system, where you will see if you are going to change the the heat there will be two scenes. One thing is that the fluid which is going to enter in the mixing process, a stir tank, and second thing is that the steam or the fluid which is going to enter by the help of the coil, they both will be affecting our system, and we will be only interested in only single output, that is the output response of the our tank, stir tank. Okay, so this type of concept that will be that we will be using there. Okay, so I think this concept is clear to all of you for today. Okay, so thanks for this lecture today. Just go and see all the video. I will be discussing lots of numerical example that is also related to either that Stephanopoulos book or the Kafner book. I will be discussing all the problems here also related to this concept. Okay, so thanks to all of you for this lecture today.